My doctoral thesis is titled Active Turbulence and Active Cell Models for Microswimmer Suspensions, and it has been directed by Dr. Ignasi Pagona-Barraga from the Department of Condensed Matter Physics at the University of Barcelona and Dr. Andrea Scagliarini from the University of Rome. My first intention, 7 years ago, was to investigate a universal mechanism from the generation of hydrodynamic turbulence. My interest was not in fluid physics per se, but in quark-gluon plasma predicted by quantum chromodynamics inside a proton moving at high velocities. I thought that the spontaneous appearance of all this complexity could be related to the vortices of hydrodynamic turbulence and that it would be possible to write a discrete, simple and universal model based on the flux of energy across the scales to explain the appearance of something like a universe into a particle. Ignasi Pagona-Barraga agreed to direct my work after reading a manuscript with my objectives and intentions. The first 2 years of the doctorate program were devoted exclusively to bibliographic research, and quickly I became interested in an emerging field of research called active matter. In this manuscript, I had discussed the GOI model, which is a classical cell model, as an appropriate theoretical framework to developing a discrete model of the relationship between different scales of a system. To explore the possibilities of this approach, Dr. Pagona-Barraga introduced me to Dr. Scagliarini, who had a beta version of a generalized cell model, and we dedicated that whole year to writing a code that captured and the general ideas of cell model and could produce testable results for active matter systems. Precisely to check the results obtained by this code, we decided to perform some simulations with Ludwig, a reputable lattice Boltzmann type code. First, we ran a lot of simulations in Albéniz, the computational cluster of fundamental physics department. And after that, we made some greater simulations with Finisterrae and Mare Nostrum supercomputers. I have to say that using supercomputers has been an amazing experience for me. It could be said, in my opinion, that these incredible machines are the particles accelerators necessary to discover the emerging structures and mechanisms of active matter. The greater the power of the machine, the smaller the range of interaction that can be solved with good resolution. The results of these direct numerical simulations turn out to be much more useful and interesting than a mere validation of cell model. So we spent about 2 years with the corresponding data processing and analysis. The last 2 years of the doctorate program were dedicated to writing the text of the thesis and 2 articles which are under editorial review for publication. And finally, today I'm a little nervous, but at the same time exciting, and very happy to be able to share with you the conclusion of this long research process. This is a presentation overview. First, I will define some essential concepts of the main topic of the thesis, active matter. I will also carry out a brief review of the theoretical framework on which the lattice-Boltzmann method is based. Next, I will present the results obtained in direct numerical simulations, running Ludwig code on different machines, as I have already mentioned before. The second part of the thesis consists of the presentation and description of a generalized cell model that is capable to produce invalidable results. Finally, some conclusions and perspectives will be listed. So, the goals of this thesis are increase knowledge about the mechanisms that generate cluster flux, collective movement, and spontaneous correlations in systems considered active matter. Study the diffusion of active particles depending on their intrinsic orientation level and concentration. Study the mechanisms that can generate active turbulence, understood as a behavior with properties similar to classic hydrodynamic turbulence through the study of energy spectra. Generalize the classic cell models to make them compatible conceptually and asymptotically with a theory of active turbulence. Propose and validate the Sabra active model and use it to study the transmission of energy through the different scales that form a system. I will begin with the description of theoretical framework and methodology. It's a clearly observable fact in nature that different forms of self-organizing motion can exhibit a number of common phenomena from mesoscopic to large scale. Comparing the movement of a school of fish, a flock of starlings, a crowd of people, or a bacteria suspension can make us think of an underlying physics that justifies this similar behavior, which is so easy to recognize and so complicated to explain. Some of these common properties are at least they are made of many interacting units where each unit consumes energy and generates motion. Cooperation occurs spontaneously and it's regulated with a relatively small set of parameters, making mesoscopic structures emerge. All these kind of systems, of course, are intrinsically out of equilibrium. Several researchers have been working in recent years in understand the fundamental mechanisms that generate the collectivity between particles, defining a new field that is known as active matter. The term active first appeared in the paper of Ramaswamy and Shima only 16 years ago and has been rapidly expanding since then. The definition places us in a sufficiently general theoretical framework to think that it is possible to expand the models and postulates of the theory of active matter to other fields outside the natural science, such as social science or economics. I have recently read the essay "The Market Has No Morals: Proposal to Save the Politics," and its author, Mathieu de César, defines the current citizen as a unit of production and consumption in the market. So, from this definition, perhaps a citizen can be considered an active particle. But what exactly is an active particle? What we can consider a particle is something difficult to specify, so that we can define active particles as each one of the components of a system considered active matter. Marchetti, in all-round review co-authored by 7 physicists, just 9 years ago, defined active matter as composed of self-driven units, active particles, each capable of converting stored or ambient free energy into systematic movement. It should be noted also that self-driven does not mean autonomous movement, because it is always subject, at least to some degree, to external forces or collective interactions. In this sense, active particles are not free particles. There are 2 essential classifications for active matter. The first distinguishes between live organisms and artificial objects. The second classification is based on the relationship between the particle and the fluid medium in which it is embedded. If there is a significant exchange of energy with the environment, maintaining the conservation of momentum, the system is called wet. If, on the other hand, the fluid is merely testimonial and the dynamics of the particle develop without significant interference from the medium, then the system is called as dry. Note that the first classification, live artificial, refers to the nature of the particle, while the second, dry wet, arises from the type of modality. Live organisms commonly move by the form in their body, something that inanimate particles cannot do. However, it is possible to swim even without external appendages and even with no deformation, just by inducing a tangential flow along the particle's surface. This kind of microswimmers are called squirmer, and this is the type of particles that we have used in our simulations. There are two relevant parameters in a squirming model equation. The coefficient B1 determines the self-propulsion velocity, and B2 is related to orientation level of the particles. The sign of B2, or equivalently of the ratio beta, determines the classification: pushers that obtain their thrust from the rear part of their body, or pullers that obtain their thrust from the front part of their body. Therefore, the parallelism or antiparallelism of the vectors determines the movement. In this image, from the article by Lauga, Evans, Ishikawa, and Yamaguchi, you can see how pullers and pushers follow clearly different dynamics, and therefore different results can be expected in some measured functions. In these images, you can also see how the beta parameter is directly related to the activity level of the particle. In the simulations carried out in this work, we will see the impact of that the variation of this parameter has on some functions of special relevance, such as the mean square displacement and the polar order, for example. Another parameter to take into account will be the concentration of particle in the fluid and its relationship with the size of the simulation, that is, the physical space that we are able to reproduce with the program. The study of the question proposed to model the active interaction between particles through the computational simulations is frequent. The level of calculation required is very high, since the simulation must include the maximum number of particles possible and the greatest range of interaction with the environment and the rest of the particles to represent the physical reality of the solution with guarantees. The lattice-Boltzmann method is a relatively new method in computational fluid dynamics that offers a very attractive way to study complex fluid flows governed by the Navier-Stokes equations, since these kind of equations are difficult to solve analytically due to the non-linearity, complicated geometry, and boundary conditions. Instead of solving the Navier-Stokes equation, the discrete Boltzmann equation is used from the simulation of collision models of a Newtonian fluid. From a long and large enough iteration of a finite number of virtual particles that propagate and collide on a grid, a microcosm of viscous fluid extrapolable to much larger masses is shown. Various types of grids, triangular or cubic, can be used in the discrete distribution function to apply the lattice-Boltzmann method. The most common way to classify its method is the form dn and qm. dn represents the n dimensions, and qm represents the m possible direction of motion at each step through the virtual particle. That is, m represents different velocities. We used a D3Q19 model in a cubic grid, like this one of the slide. Ludwig is a code based on the lattice-Boltzmann method for simulating complex three-dimensional fluids through a set of routines and communications. With this code, it is possible to configure multiple models with different values of free energy and other parameters. This is a particularly interesting code because given the relative simplicity of execution in relation to the power of simulation, is ideal to be able to draw physical conclusions without having to deal with a complicated programming situation, so that the user may concentrate on the physics of the problem rather than on parallel computing issues. Ludwig is structured as a library of pre-configured models that can be affected at the parametric level through the input file. The underlying physics is within the framework of active nematics. Now it's time to present the results obtained within direct numerical simulations. This study was performed from the results of several simulations with Ludwig code with a size of 400,000 iterations at least, carried out in the Albéniz cluster of Fundamental Physics Department of Barcelona University. We want to explore the parameter space phi beta, where phi is the volume fraction for n spheric colloids, spheric squirmers, with radius 2.5 into a cubic grid of length equal to 128 units. As I have said before, the initial objective of this simulation was to validate the results of the cell model, which I will explain in the next part of the presentation. Remember that beta is the ratio between B1, which corresponds to a parameter of the self-propelled particle's velocity, and B2 corresponds to a parameter of particles' orientation. From the logarithmic representation of the four curves with B1 equal to 0.01 and different values of beta, plus minus 1, plus minus 10, obtained by varying B2, it is easy to observe, as would be expected, a linear growth of the mean square displacement, calculated with this function. Increasing the orientation level also results in an increase of mean square displacement. Nevertheless, a surprising result is found in the calculation of the mean square displacement for different concentrations phi, keeping the absolute value of beta equal to 1. It can be seen that for low concentrations, specifically for phi equal to 0.012, 0.03, and 0.06, and only in the Puller's case, there is a big difference compared to the rest. I refer to these curves, yellow, red, and purple. Also notable is the fact that there is a strong asymmetry between pullers and pushers. Likewise, for the same lowest concentration, phi equal to 0.012, by increasing beta to plus minus 5 through the orientation parameter B2, any change in increasing trend of mean square displacement disappears. This curious phenomenon occurred recurrently at the same point in the parameter space phi beta, no matter how many times we repeat the simulations. This fact made us no longer treat this data as a simple validation, and they began to have interest in themselves. We can see here highlighted the four cases of relevance, taking as a reference the concentration 0.12 that presents the regular situations, This is a diffusive type behavior with an exponent close to 1. However, the simulation for phi equal to 0.012 shows of a ballistic type behavior with an exponent equal to 2, and even more so, the simulations corresponding to pullers with concentration 0.03 and 0.06 have large exponents and therefore exhibit a behavior that we could call superballistic type. To better understand the slope change explaining and assuming that a higher orientation level favors the displacement of the particles, the mean orientation P is calculated for different beta and phi values according to these expressions, where the vector E represents a three-dimensional orientation vector of a particle at an execution time step. At long times, the suspension reaches a steady state called polar order. Polar order equal to 1 represents a completely polarized system, while a isotropically orientation reaches this expression. Observing again the curves yellow, red, and purple, it can be seen that simulations that behave differently from the rest in regards of mean square displacement also behave differently for the polar order. These simulations have a much longer transitory state, reaching a value of the mean square orientation much higher than the rest. Longer simulations, around 1 million iterations, were necessary to reach the steady state and place us at orientation levels of 0.5, 0.6, and 0.2 respectively. It should be noted that the levels of orientation in superballistic behaviors are much higher than the level reached in the simulation phi equal to 0.012, which remained in purely ballistic behavior. The fact is that a degree of order has been generated spontaneously, not through the execution parameters of the program, and this extra degree of orientation greatly facilitates the displacement of the particles as they are dragged by the fluid, and it can be even observed that the greater this degree of order, the greater the value of the displacement capacity. Regarding the increase in polar order, other researchers, such as Dr. Francisco Alarcón from the University of Guanajuato, Mexico, published similar results for similar concentrations a few years ago. On the next slide, we can see the results obtained in a simulation carried out in Mare Nostrum for a concentration of 0.06 with beta equal to 1, which is a case of interest. In the first image, we see the evolution of the local slope and the mean square displacement up to long values of time, reaching up to 5 million iterations in the program. Simulating such a long evolution allows us to observe two crossover points. Firstly, we see an increase in the local slope towards values compatible with ballistic behavior, and subsequently decay towards values close to 1, compatible with diffusive behavior. In the second image, it can be observed, as we have seen before, that the change in the local slope is associated with an increase in the level of order that for a long time reached a steady state close to 0.3. This study confirms the behavior observed for a grid of size 128 and assures us that no more oscillations occur, considering the stationary state obtained as stable and definitive in the system. By the way, these graphs are included in one of the articles. Next, we will analyze how the size of the grid affects the results. For this, a simulation has been carried out in the machine Mare Nostrum of BSc with a grid of size 500, 512, 512, 512, and concentration 0.012, 0.06, 0.12, with beta equal to 1 or minus 5. As can be seen in the figures on the left, the increase in the size of the grid seemed to change some substantial aspect in the behavior of the particles in terms of displacement dynamics. The figures corresponding to a concentration 0.06 and beta equal to 1 for grid size 512 and 256. These curves show a local slope equal to 2 when, in the case 128, for the same concentration and values B1 and B2, the slope was significantly larger. Even despite this quantitative difference, qualitatively, it should be noted that there is still a clear deviation from the linear growth of mean square displacement for this concentration in all grid size. It can be seen here in the inset of the figures that the polar order increased to values close to 0.5 in the three sides of the grid, from 128 to 512. The figures on the right correspond to concentrations 0.06, 0.012, and 0.12, with beta equal to minus 5, changing the B2 from 0.01, as in the previous figures, to minus 0.05. In these cases, the local slope is close to 1, like most of the analogous curves presented earlier in the figures at the smaller grid. Therefore, no significant effect is observed in the behavior due to the size of the grid in the simulation. In the next frame, we can see as the energy spectrums of the simulations are analyzed in order to find indication of energy flows through the different scales, represented by different values of key in the Fourier space. In particular, the flow from the smallest scales, such as high values of key, towards the largest scales, known as the inverse cascade phenomenon. As a signature of turbulence, we expect to observe that as the volume fraction decreasing the Reynolds number, the energy spectrum at low wave numbers should be broadened, distributing the energy of the system in an increasingly homogeneous way through an increasing range of scales until reaching the diffusive level where a sudden fall will occur. However, in the first figure on the left, no significant difference are observed when we vary the concentration for beta values plus minus 1. Therefore, there are no indications of an inverse cascade for lower concentrations, and no difference in behavior between pullers and pushers are observed either. In the second figure on the left, for a concentration of 0.012, you can see widening of the low frequency region when increasing the beta parameter from 1 to 5 in absolute value, which can be interpreted as a low incidence of the inverse cascade when increasing the level of orientation. In this case, there are small differences in the behavior between pullers and pushers also. We analyze how the size of the grid affects the results by a great simulation carried out in Mare Nostrum. With a grid of size 256 and a concentration 0.06 and a beta value equal to 1. We ran the simulation until 2 million time steps. No significant changes are observed with respect to the previous cases, where the size of the grid was smaller. The most notable fact is the value -3 in the local slope of the spectrum in the inertial range, which turns out to be a value in agreement with the theoretical prediction, and that will also obtain it with the cell model. In fact, this will be the result that we will use to validate our model's subaractive model, that I will explain in the next section of this presentation. This image is a simulation for a grid of size 512 included in one of our articles. We can see represented the energy spectrum, time averaged over the statistically stationary state of the fluid velocity field normalized by the mean square velocity in a suspension of pushers, beta equal to -5, at a volume fraction more or less 0.1. The solid lines indicates one more time the scaling key -3. The inset is a snapshot of the velocity field in the plane. Notice the size of correlated region as compared to the microswimmer size. In particular, the occurrence of a jet is highlighted by the green ellipse. In the last part of the presentation, I will talk about cell models. Cell models are deterministic dynamical systems based on a discrete interaction of different modes of the same function. This highly repeated self-action aims to reproduce the essential features of complex continuous systems, reducing the complexity of the full field equations. In no case does the cell model try to model any physical reality. That is, it is not intended to be a mathematical description of a certain phenomenon of dynamics, but rather they offer the possibility to investigate the chaotic dynamics and multi-scale correlation of turbulence with obvious computational advantage and sometimes even amenability of analytic training, being a tool capable of producing universal applicable results. The great advantage of cell models is their simplicity and their great versatility to introduce greater or lesser complexity into the equations, allowing the effect of each term or function added to the model to be quantified. In essence, they allow us to model the ingredients of the underlying fundamental physics shared by a huge set of natural systems. The original cell model is GOI model. Basis of this cell model is found in the Gletscher's article, and it is based on the Obukov 1971 equations, which are published 2 years earlier to try to describe ocean mechanics. Yamada and Okitani's articles, 10 years after the publication of the Gletscher's article, proposing an improvement of this model using a complex variable, as we can see in the slide. In fact, the name in the frame. In fact, the name of the model includes the initials of the three authors, Gletscher, Yamada, and Okitani. The point is that it is a turbulent cell model which has a low chaotic attractor, which has statistical properties similar to real inertial turbulence, but as I said before, equations of the cell model do not carry any of the geometrical information contained in the original system. Describing the time evolution of the complex variable, U, that can be though as a sort of Fourier amplitudes of velocity fluctuations over a length scale with associated wave number k, the general equations governing the process are a system that links each equation corresponding to a given cell with its predecessor and successor by the function g. There are two conserved quadratic integrals that are physically identified by energy and vorticity. Subsequently, the works of Yamada, Gletscher, and Okitani, other authors introduce a modification in the GOI model that affects the number of complex conjugate operators, but not the fundamental properties of the model. This improved model is called Sabra model and is given by this function in terms of structure functions. You can see that the mixer functions phi is similar to the previous one, g, but not exactly the same. So, Sabra model will behave analogously to GOI model in terms of scaling law. This statement is supported by the results of several numerical simulations published in the literature. This balanced equation describes the steady state as a competition between the energy flow from the upper to the lower scales and the energy flow in the opposite direction. In the inertial range, the term with coefficient c is offset by the first two terms with coefficients a and b, since the viscosity is zero and the force only acts on the upper scales. In the viscous range, that is for scales below the Kolmogorov scale, the term with coefficient c is offset by the viscous term, which acts as a cutoff because the structure functions of free order of coefficients a and b go to zero quickly in this part of the spectrum. Within the inertial regime, with no input or loss of energy, the total energy of the system must be conserved, and therefore the total variation of the energy must be zero. So we have to impose the condition A plus B minus C equal to 0. From this condition that links the parameters A, B, C, we can reduce the parametration to a single epsilon value. The P function can be used to model energy flow even in terms of the balance function C. And we can use it to rewrite the Sabra model equation, emphasizing this dynamic of competition between energy flows in the direct and inverse directions. The final form of the equations would be an unstable equilibrium which reflects the basic characteristics of the turbulent regime, and we will use to represent the dynamics of active turbulence. The function phi f represents a forward energy flow, such as a direct cascade, and the function phi b represents a backward flow, such as an inverse cascade. If lambda is equal to 1, a regime of direct cascade is obtained, and if lambda is equal to 0, an inverse cascade regime is obtained. Any other value of lambda in the interval 0, 1 gives a mixed dynamics. The term minus gamma c is a self-advection term determined by the relaxation time of the system. The generalized version of the Sabra model, which has been developed in this doctoral thesis, is based on relating two fields instead of one as usual through this function. With respect to the model equations, P represents an order parameter quantifying the degree of local orientation. U represents the velocity field relative to the general motion of the fluid. the active stress sigma appearing in the Navier-Stokes equation and quantifies in some sense the level of activity. Omega denotes the antisymmetric part of the velocity gradient tensor. Eta and D are the fluid dynamic viscosity and the orientation field diffusion coefficient respectively. From the general form of the model equations, a cell model can be formulated, but the appropriate form of the terms must be chosen. Each term can refer to the interaction or self-action of the two fields involved and can generate an energy flow in two directions, towards large values of key or towards small values, defined through a critical value of epsilon. Different choices, variation or combinations of the terms will presumably produce different results, and in fact, the study of all these possibilities is a line of research of interest for the future. From a first formal inspection of the equations proposed by the model, the following characteristics can be deduced. We enforce a zero Reynolds number regime and don't account for nonlinear momentum transfers. We take the function phi uu equal to 0. The linear damping term stems from dissipation in equation nu acts only on intermediate and small scales. Large-scale drag coefficient mimicking friction with the boundaries is actually represented by the term like mu k minus 4. The divergence of the active stress is described by a force in terms of P. We conjecture that the rotation term P gradient of U is the one responsible of the upwards energy transfers, such as inverse cascade. On the other hand, the advective term U gradient of P and self-advective P gradient of P terms have mixing properties that should tend to disrupt spatial coherence of orientation and therefore to transfer downwards, such as Dirac cascade. In the figures below, we can see a numerical validation of these last assumptions. From a coarse graining procedure, a function phi f interpretable as a spectral flow is calculated and a clear qualitative difference appears. While in the cases advective and self-advective, there are negative values at intermediate and large wave numbers, signaling that they transfer orientation fluctuations towards small scales, the rotational spectral flux is always positive. The equations at the top of the frame are the final form of the model after the numerical assumptions that I have described previously. Superindex B and F represents backward and forward energy transfer respectively. Finally, these figures shows the results of a simulation carried out with implementation of the supraactive equations in a code. We can see that the energy spectrum develops the case with the power law K-3 over a range of intermediate wave numbers, as can be theoretically predicted and exactly as we saw in the direct numerical simulations. The dynamic equations of our cell model are similar to Sabran model equations, but also try to reproduce or at least capture the essence of the self-action of the particles and the movement of the fluid which surrounds and transports them, with the P field and U field respectively. Therefore, these equations can be related to the study of active matter, and this is the reason why we refer to this model as supraactive model for active turbulence modeling. And now it's time to list the main conclusions of this work. The variation of the concentration phi caused significant increase of the mean square displacement linked to a strong growth in the polar order for pullers. Under some parametric circumstances, the system relaxes by transforming internal energy into kinetic energy through an overordering of particles, encouraging them to flow without colliding with each other while being dragged by the fluid. There is a flow of energy from the upper scales to the lower scales called direct cascade. Likewise, there is also the inverse cascade, that is the flow of energy in the opposite direction. Both energy currents are in a competitive regime. Sabra active model is tested for the first time in this doctoral thesis. The results generated by the simulations with this code are compatible with the results obtained by the lattice-Boltzmann method and according to the theoretical predictions. Thinking about the future, the main lines of research interesting for us are that we consider it necessary to continue investigating the processes that regulate active systems, both at parametric and dynamical level, using the Sabra active model. We shall continue with the search of structures and groups formed intrinsically by the system as clusters of flux. Detection of intermittency signatures in the cell model simulation is intriguing and shall motivate further computational studies. It will be interesting to do quantitative tests of how actually turbulent is active turbulence, allowing to measure on much longer runs. It will also of great interest to add new terms to Sabra active equations and study their impact on the results and explore other types of active systems. At this moment, we have 2 articles written based on the research and conclusions obtained in this doctoral thesis. The first focuses on the dynamic aspects discussed in the section referring to direct numerical simulations in everything that refers to the variation of the parameters beta and phi, polar order, etc. The second focuses on the energy spectrum and application of the Sabra active model. Both are currently undergoing editorial review. And to finish, I would like to thank my director, Dr. Ignasi Pagona Barraga, for his explanation and his guide through the process of creating this doctoral thesis. I want to thank to my director, Dr. Andreas Caglerini, for his great help and carrying out this thesis at a technical and theoretical level. And that's all. Thank you for your attention.